That's great. Pedro is Technical Director at FCT Combustion, with over 25 years experience in the cement, industrial minerals, lime and fertilizer industries. He's held both managerial and technical positions across Latin America with a degree in chemical engineering. He's also a master's in NOx emissions reduction in clinker kilns, holds a number of patents, and has developed novel processing routes for a KTO-based fertilizer. Pedro is an experienced pyroprocess technician, currently focusing on sustainability projects, engineering, R&D, product development, and optimization. So really highly qualified for this presentation. It's great to have you back, Pedro, for this presentation. Over to you.
Thanks, Thomas. It's always good to be here. I'm going to jump quickly into the presentation. Just a quick overview about the company. FCT provides solutions for the cement industry in so many different areas, from grinding to calcining to drying, burners and burner management systems. And also we are putting a lot of focus on the calcine clay business. We serve not only cement but iron ore. We go into lime, pulp, paper, mining, and other mineral industries. And the good thing about this is we can use technologies from one industry to the others, and we can really gather a lot of information and learning from each of them. Well, so we are in very different places, from clay calcination to the cement kiln burners and hot gas generators and so on. It's like in pelletization of iron ore, for example. Different clients, we have all sorts of clients from different origins, and we are spread all over the world. We have offices in Adelaide, in Nanjing, in Vienna, in Brazil, in Sao Paulo, and Fort Lauderdale in the US. So you can pretty much reach us in any part of the world. And the topic here is the reduction of CO2 footprint in the cement industry through process optimization. I was thinking how to introduce the topic, and I would say, well, probably the easiest way to say is that process optimization is equal CO2 reduction. If you do things properly, if you reduce consumption, if you increase the efficiency of a cement mill separator or a grinding media, or anything that is related to that, you're certainly going to go and reduce CO2. But although it's quite a generic statement, I will just go into ask for some help from the roadmap to carbon neutrality from the Portland Cement Association in the US. And they have split this into 3 sections, one being at the cement plant with different topics and areas of opportunity for increasing efficiency and reducing CO2 emissions. And then you go into the construction, designing and building, and then you go into the concrete infrastructure already in use. So all these 3 could cover different opportunities for CO2 reduction, but let us focus for a while on the first one, which is at the cement plant. So the pathway for carbon neutrality goes along with the use of alternative fuels, continuous efficiency improvement, carbon capture, clinker improvement, and promotion of SCM and TCO. So first we start with alternative fuels. I just put here a picture where we can see the heat value of all fuels is really going down, and the majority of it being based on less traditional fuels and more alternative fuel, different sorts of alternative fuels, and the challenge that's posed to us those days of using all sorts of materials in the fabrication. So sometimes when you do that, the first thing you notice is that you start building rings or balls or weird things going inside the kiln due to poor combustion and circulation phenomena, a lot of sulfur flying over, and then condensation and so on. And this can be a disaster from the health and safety, but also from the performance of the main pieces of equipment like the kiln and the heat consumption and so on, and loss in productivity and production and sales. So that can be quite a bit of a challenge. And the way to tackle that, I can give you a summary being, you have to promote early ignition. So if you have a main flame, the main burner, you might be able to quickly start the ignition in the first meter or even less than a meter from the burner tip, even using difficult to burn fuels like alternative fuels. So what we are looking for here is how to get to this early ignition. One would be, well, looking at the design of the burner, the traditional burner goes with an axial air and then solid fuels and through air. And you can give it a different configuration. As you can see here, axial air has a different pattern of distribution and area, but the total area of air is the same, and you can do it in 3 different ways, from grouping them with big holes or small holes, all well distributed. And it will influence the shape of the flame and how early you can start ignition. So this is for the same area, the same impulsion or momentum of the burner, but if you arrange it differently, you might have different results. So one being the 36 even, we made a simulation showing how does the heat flow distributes along the kiln, and it's kind of concentrated here, but if you just change it for this configuration, bigger holes, and at least less number of holes, but with bigger area, double as much. So this will give you a higher peak of radiation and more heat transfer, more concentration, which means a more robust flame. And if you go in then with the same number of holes, and then but now they're grouped together, and then you might experience even higher peak, which means you have a more robust and compact flame, more prone for a higher quality clinker. So what we've been doing based on that is trying to use both configuration altogether, trying to use this concept whenever it's not necessary to have such a very concentrated flame. And then if you want to do this, we put together this in one single equipment, which turns out that we can run it with air through the small holes or without air in the small holes. So depending on how much you want to shape the flame closer to the burner, depending on the amount of alternative fuels, you might need this flame. If you're not running so high alternative fuels, you might use this one instead. So one compensates for the poor ignition and the other one does not. So in the end, you get the same flame in different configurations and different amounts of alternative fuel being used. So when you look at this, the burner looks like this. As you can see here, most of the secondary area is going to be entrained through this area here. Whenever you keep this low, it's going to be even more secondary air. And when you see it from the back, the burner gets a bit more complex in terms of configuration, but you give you more flexibility to really format the flame, they shape it the way you want it. The other thing you can do whenever you were spraying or you're injecting alternative fuels, you can give it a bit of a swirl. By swirling it a bit more, the dispersion of alternative fuel will allow you to burn even earlier than if it was not dispersed. So by swirling the injection point, you're probably going to be able to have a much robust flame, meaning that you're going to have a less problem with sulfur recirculation, to name one. So you can do this with a brand new one, but you can use an existing burners. As you can see here, this originally was a burner from the competition, and then we wanted to change part of it. So we tapped a bit some of the holes you have here, and then you promote this higher entrainment in the secondary air, while changing here the configuration of the swirl to promote even more mixing and a better flame. So this was a very successful project, very cheap to be installed, and finally they got the result they wanted just by changing some principles or the geometry in the burner tip. So again, it's all about early ignition, as you can see here. And as a result of those blind points here where the secondary air enters, here you can see here kind of stripes, where here you have all the secondary air coming in, and then you have a very early emission, so we promote this very good combustion. Basically what we do, we made it to measure. So what we do, we shape the flame, we shape the burner according to the client's needs, the types of fuels and amounts and so on. So you're gonna have your own burner for your application. The second topic would be continuous efficiency improvement. On this one, I really reminds me of my time when I worked for the cement company, where I used to be a process engineer, and I have this this feeling that everything goes along with the process engineer, and process engineer is that guy that is continuously measuring, for example, the granulometry of the clinker. So depending on the granulometry, you can recover more or less secondary air. More secondary air means that you have a lower heat consumption, less loss in heat through product, and then you can really recuperate heat. So it all depends on the granulometry, which by itself depends on the coating conditions, the clinker modeling, and the burnability of the material. So one of the most important things is to know the chemistry. When you know the chemistry, you can maintain this granulometry, recover more heat, have a more stable kiln, a more stable coating, and a longer campaign. So all because you're really managing the chemistry. And as a result, of course, you might reduce CO2 emissions because you're running at improved heat consumption. The other thing you can do, you can have a look at your calciner and see if you're injecting fuel only on one side, and you put together a CFD model, and you see that as something that we do also, and you see that the fuel distribution is uneven, so you have high oxygen, low oxygen, poor combustion, and you can have an even distribution of fuels by injecting 2 different points or 3, 4 different points. You can get better results, earlier heat exchange, and then lower temperatures on the preheated exit, which means lower heat consumption, by which in turn means a reduction in CO2 emissions. And then you have all sorts of possible distribution and patterns, and the way you regulate the flows and how you swirl the flows to get a good and proper combustion. Also, as a result of a good flame and a good burning early ignition, you might have a short flame. By short flame, you mean in the end you have a smaller halides, and by having smaller halides, you're going to probably have better efficiency and better concrete properties, and you can use even less clinker and substitute with other cementitious material, and then you reduce CO2. And also in the burnability, it's the same. When you put together the right configuration of the chemical modeling, you might be able to really improve the burnability, and by improving burnability, you reduce the temperature where the material is being processed, and then you again reduce heat consumption. When you know what you're doing and you balance all the elements entering the kiln, you can really get to an equilibrium between sulfur and alkali, and by that you can reduce the sulfur cycles, and then you can prevent the formation of rings and all this difficulty you may have in the process. And well, also you can prevent yourself from clogging the preheater, and really control the internal cycles of those nasty elements that used to have in the cement industry, in the clinker kiln. So the other two would be carbon capture, something that we are not addressing in this presentation, and clinker improvement. We sort of talked a bit about this, but we go straight to the promotion of LCM. LCM being that we are starting from the traditional cement, Portland cement, 95%, 5% gypsum, and the opportunity of not having CO2 is only on the 5%. All the other one is CO2 intensive, coming from the decomposition of carbonates, but also from the combustion of fuel. So there's a lot of CO2 involved in this portion here. we cannot really say no CO2 because there's a minor amount of CO2 being emitted for the fact that you are bringing in gypsum and you are mining it and so on. But again, you can use all sorts of substitute elements for the composition on cement, and if you do that, you can go from this configuration through something like 50% clinker, calcined clay, limestone, and gypsum. So here you really are relatively low to no CO2. Again, this one has less CO2 because it doesn't have the carbonation taking place. So all the CO2 will be reported as a fuel CO2 for this one, and the one coming originally from clinker. So you reduce the total amount of CO2. So when we go into looking at this calcined clay, that can be a big chunk of the reduction. We're looking to synthetic pozzolans. Hopefully, I wish we had natural pozzolans all over the place, but we do not have it. So we get material when we heat treat it, the clays, and fortunately, the temperature they need for the dehydroxylation ranges from 600 to 900, which was relatively low, and you can produce nice metakaolin out of it. So instead of producing C2S, C3S, we are producing AS2, a good substitute, which has low to no CO2 coming from the raw material. Now, what we typically do, we map the material, we see where it loses moisture, when we activate the clay, and where it starts to crystallize. We'd like to have material that is pretty much amorphous. We don't like it to be crystallized, so we should reach a temperature where all the activation takes place, but then you stop it in a certain temperature to prevent the material to crystallize from crystallizing. Well, FCT has two technologies for clay activation, one being the flash calciner and the other one being the rotary kiln. We don't prefer one over the other. We just look in case by case which one is the best fit for your process. Different configurations, you can run the preheater or the flash calciner with a hot gas generator, and then you have a dryer. You have to dry the clay before entering the tower. So finally, we can use very flexible combustion systems like hot gas generators, and you can introduce a lot of biomass, alternative fuels, and even coarse fuels. So what we know, it's always the first question whenever you're talking about clay, what about the color? Clays can have different colors originally. After they are activated, they can become red, or the cement can become pink. We know this pinkness, there's no correlation with cement performance, although the market acceptance for pink cement or red hue cement is really limited. So we must try and control the hematite and try to get as much magnetite and prevent it from being the ion being reported in this more oxidized form. So different ways of doing that, but basically what is being done lately is to control the atmosphere inside the kiln and during the cooling. One of the first of the traditional methods is to promote a reducing condition. You reduce the oxygen available to oxidize magnetite, or you keep the oxygen low. It can be fuel in the feed, or it can be fuel in the kiln discharge. The good thing about using those methods here is that it's relatively low in capex, but the cons is that probably all the fuel you're putting in the feed, it's going to be lost. So you increase the overall heat consumption. You might be also facing an increase in VOC and CO emissions. So good, but it's cheap to be installed, but probably you're going to pay an important fee for running with this configuration. If we go for quenching instead of we try and keep the ion as magnetite, which is the form of ion that only occurs at higher temperature. When you come down with the temperature, it becomes hematite again, and we try to freeze it as magnetite just by quenching. You might use water spray in the kiln discharge, or you can use indirect cooling. That might be depending on the configuration. Low capex, I leave a question mark here because normally indirect cooling is not the cheapest option. So, but either way, you will increase heat consumption and electrical consumption by you applying this methodology. And there is one, there is a patent development from FCT. We call it the inorganic modifiers. Basically, what we do, we're trying to source in your quarry elements that could immobilize the magnetite. So if we can bind the hematite, the magnetite with something and preventing it from becoming hematite, we can probably control color. So the action is to determine the most suitable reactant to bind with magnetite and preventing it from becoming hematite again. And what we see as one of the most important pros is that you normally have an improvement in the concrete properties, one of which is you reduce blame. By reducing blame, you know that the water demand is going to be lower, so the demand for plasticizer reduces and so on. What is cons? Well, we cannot say it. It's a case-by-case evaluation, but generally speaking, in terms of CO2 footprint compared with the other methods, we're better off in this one. So we can provide it with pilot plants. We have a flash calcination in Brazil. It's a flash calcining mountain in 2 containers. It operates. We've been doing a lot in this for scale up and to provide solutions for our clients. It's basically a hot gas generator, a calciner loop, and then we quench the material with air and get product from it. And we also have a rotary kiln calcination. It's a sizable pilot plant. We have also, so we can submit your product for testing in our facility, so we can have the proof and the collect data needed for the scale up. This is when you do muffle calcination, oxidizing way and in different temperatures, but when you flash it in the high temperature with the right inorganic modifier, you can have a pretty dark product. So the same happens from when you get the ore and you muffle calcine it, it gets red. When you flash calcine, we can get the material with less of this red hue. This is a quick video showing the utilization of inorganic modifiers. You simply mix the inorganic modifiers along with the feed, and you can see here the material is not even ground. It's just volumetrically added to the feed. It's being processed in the rotary kiln at very high temperatures. And this one is it's fired with diesel, high oxygen content in the kiln atmosphere, so there's no oxygen control or any depletion of oxygen here. But as you can see here, the product becomes gray because of this interaction of the reaction between the inorganic modifier and the clay. So we succeeded on doing the right color control. This one was a very, very high content ion, over say 15% of iron oxide in the raw material, and we managed to get the gray color despite oxidizing conditions in the kiln and not using water, not using any special fuel to do that. And the product become like this, and when we get from the original clay into the calcined clay and the cement afterwards, you can see here very low A numbers, which one of those that we use to measure color in terms of red. So pretty much what I was trying to say is that there are different methods of reducing emissions of CO2, but bear in mind that you have to keep yourself technical and very skillful process engineering team in your plant. You have to have the right burner, not only with a high impulse, but also a high impulse and the right configuration of the air, so we can form it and shape the flame. And you can use novel technologies to control color with a good, reasonable good footprint and get the results you need. So basically what I tried to cover on this one was those aspects of alternative fuels, continuous efficiency improvement, and the promotion of substitutions for the cement industry. So, well, thanks a lot for your time, your patience, and I'm here for any questions.
Thank you very much, Pedro. That was a great overview of the classic decarbonisation technologies, starting with the pyro process and the burner design and fluid dynamics being used to improve performance. Just a general question about the burners. If a plant is transitioning from, say, 5% alternative fuels to 25%, is one burner enough to cover that scope, or do you need different burners when you're moving to quite different levels of alternative fuel utilization?
Depends on what you already have as a hardware. If it's a relatively new burner with a good configuration, you can just tweak it to some extent. You can probably change from a fan to a blower and get a different configuration, and you're ready to go. Sometimes you need to add an injection pipe and may not fit into the burner body. You might have to put a satellite burner or put something on top of the burner, or you can completely reconfigure your system. So it will depend. But yes, normally the message here is it may be possible to reutilize whatever you have and just tweak it. But sometimes it's just it doesn't pay the price. So you probably have to completely change it.
Mm-hmm. Okay. A question here on the burner: how much fuel consumption can be reduced using one of the burners? So in terms of kilocal per kg of clinker.
So yeah, if you're affected by the inlet temperature of the kiln, where you have a very lazy flame, and then you're losing through the exhaust gases some of the heat, it might be impressive. In some cases, might be minor. But normally, the overall reduction is not only on the heat consumption, but when you get the right crystals, the right halide crystals in clinker, you might even save on grinding as well. So it will go case by case again, but it can be very, very beneficial for different reasons, including grinding. And of course, if you have a more concentrated flame, you might be able to produce higher quality and utilize more substitution of clinker as well. So many benefits. It's difficult to tell one. It's more case by case.
Okay. Quite a few questions about calcined clay. A lot of interest in that. You highlighted the two systems, flash calcine and rotary kiln. It's clear that the rotary kiln, these can also be conversions of existing kilns. I was just wondering, can you convert an existing preheater into a flash calciner, or is that not something that's been tried?
We made this exercise, but normally the flash calciner has one zone that's for preheating, the other one for calcination, the other one for cooling. So it's hard to fit all these three zones in an existing plant. So normally it's better to make a more compact and made to suit instead of reutilizing the preheater. You might be using the building as a support, but probably not the preheater itself.
Okay. And in terms of the actual process, question here: when using reducing conditions to manage the clay color, does that affect the cement performance?
Yeah, indeed. You might have problems like, for example, you have a long flame as a consequence of this reducing condition. You delay the combustion. You might have problems with that. And yes, in many ways you can have trouble with that.
And also calcined clays normally have higher water demand. How does that affect the concrete or cement strength?
Yeah, a lot. I mean, a lot. Just water demand means that you're going to add and lose strength of the concrete. So you may manage this by plasticizers. So you pretty much substitute part of the water. And the other thing you can do, you can provoke to some extent some sintering some reduction in the blame, and then you can succeed in having the right blame for it. So you can compensate for that.
Okay, so you can compensate for those weaknesses.
Correct.
Yeah. Okay, well, thank you very much, Pedro. There are a few more questions if you want to have a look in the Q&A, but we better move on.